6 times now, the inductive biases series stopped at the same door. Every time the gradients came up, the narration said the same thing. How the gradients actually flow through the layers is its own from scratch series, coming later. This is that series. And this is that episode. Today we open the door, and there is nothing behind it but the chain rule and some careful bookkeeping.
But isn't this just AutoGrad? Doesn't the framework build a graph and differentiate it for you?
That is exactly the belief we are here to take apart. There is no tape. There is no graph being recorded behind your back. In this library, every layer carries a handwritten method called backward. And that method is the derivative, written out by a person who understood the layer. AutoGrad would automate what we are about to do by hand. To trust it, you first have to see that the by hand version is not magic at all. Here is the whole shape of it. Think of backpropagation as a relay. A gradient arrives at a layer from the layer above, telling it how the loss reacts to this layer's output. Hold this picture in place. The layer does 2 jobs with that incoming gradient. If it owns any parameters, it records how the loss reacts to them. Then it passes a new gradient downward, telling the layer below how the loss reacts to its output. That is the chain rule as a software protocol. Gradient in from above, gradient out to below, and a note kept on this layer's own parameters along the way. Every layer in the library answers to one small contract: a forward, a backward, and a list of its parameters. The next scenes are not random bits of code. They are just different layers answering this same contract. Start with the simplest layer that owns weights, the linear layer. Its forward pass is an affine map. Each output is a weighted sum of the inputs, plus a bias. Notice one small thing it does on the way through. It caches the input it was handed, the symbol X. It will need that input again on the way back, and this is the whole trick of backpropagation. The forward pass leaves behind exactly what the backward pass will ask for. Now keep the method inside its class before we stare at the body. This is linear, a layer object with weights, biases, a forward method, and a backward method. The argument named G is not arbitrary. It is the gradient arriving from the layer above. One number for each output of this linear layer, telling us how the loss changes when that output changes. And self.x is the input saved by the forward pass. If the layer had 2 inputs and 3 outputs, self.x has 2 entries, while G has 3 entries. The backward method is where those 2 pieces meet. Before code, write the chain rule. Each output coordinate is y sub I equals the row of weights for that output, dotted with x, plus the bias for that output. A single weight wij only touches output I, and it touches it by multiplying input xj. So the loss gradient on that weight is the incoming gradient gi times xj. The bias is easier. Yi changes 1 for 1 with bi, so its gradient is just gi. The returned gradient is the one for the previous layer. Input xj fed every output, so we add up, across all outputs, weight wij times incoming gradient gi. In matrix language, that last line is double, U transpose times G, but the loop version is easier to see first. Here is the same backward pass written a little more pedagogically than the compact source version. The outer loop chooses an output coordinate, output 0, output 1, output 2. The variable grad out is the piece of G for that output. The inner loop walks across the inputs that fed that output. For every pair, output I and input j, the weight gradient receives grad out times xj. At the same time, the input gradient we will return receives that weight times grad out. That return value is the part people often lose. Backward is not done when this layer knows how to change its own weights. It must also hand the previous layer its gradient, so the relay can keep moving downward. The source can pack that return into a list comprehension, but conceptually, it is just the accumulated W transpose times G.
One thing looks odd: the weight gradient uses A plus equals, not a plain equals. Why add into it?
Good eye, and that plus equals is the most important character on the screen. A weight is used once per example, but we train on many examples in a batch. Each example has its own opinion about how that weight should change, and we want the total. So each backward pass adds its contribution on top of what is already there, and we reset the running total to 0 only when the batch is done. A shared parameter answers to every place it was used. Hold onto that idea. When a single weight gets reused across many positions, later in this series, that same plus equals is exactly what makes weight sharing work. Before we zoom into one line of code, keep the object around it on screen. This backward method belongs to the hyperbolic tangent layer, a real layer object sitting between two linear layers. It does not own weights, so it has no parameter gradients to store. But it still has the same contract as every other layer: forward on the way up, backward on the way down. Forward, the hyperbolic tangent is almost nothing. Squash every number into the range from -1 to 1, one component at a time. And like the linear layer, it caches something for later. Not its input this time, but its output, the squashed values themselves. That cache is why the backward method can be so short without being mysterious.
Why keep the output instead of the input? Every layer seems to cache something different.
Because of a small gift from calculus. The derivative of the hyperbolic tangent can be written using the tangent itself. It is 1 minus the output squared. So if we already have the output sitting in the cache, the backward pass needs no new evaluation at all. It takes the incoming gradient and multiplies it, component by component, by 1 minus each output squared. That is the entire backward method on this layer, one line. The activation has no parameters to record, so it only has to pass a gradient down, and it scales that gradient by how steep the squash was at each point. Where the tangent had flattened out, near plus or -1, that factor is nearly 0, and almost no gradient gets through. That is not a bug in our code. It is a real property of this activation, and it has a name you will meet again. When a deep stack of these squashes multiplies many small factors together, the gradient can shrink toward nothing before it reaches the bottom layers. It is the reason later episodes reach for an activation with a flat derivative of 1, the rectified linear unit, and it is the kind of thing you only truly understand once you have written the backward pass yourself and watched where the signal dies. We have two layers that each know how to hand a gradient downward. Now we chain them. Where does the very first gradient come from? From the loss. Episode 1 ended on a fact that feels like a gift right here. For every one of the standard losses, the gradient at the network's raw outputs is simply the prediction minus the target. The residual. That residual is the seed. It is the gradient at the very top, before any layer has touched it. It has one number for each output the network produced, how much the loss wants that output nudged, and in which direction. Everything that follows is just that vector, being handed down the stack and reshaped by each layer it passes through.
Is the reverse order the whole secret? Just run the layers backwards.
That is genuinely most of it. From that seed, the network's backward pass is 5 lines, and it reads like the relay we described. Ask the loss for the starting gradient. Then walk the layers in reverse order, handing each one the gradient and letting it return the next. The last layer goes first, because on the way back we are undoing the forward pass in the opposite order it was built. Each call quietly records that layer's parameter gradients as a side effect, and returns the gradient meant for the layer below. When the loop reaches the bottom, every parameter in the network is holding its gradient, and we never wrote a single derivative twice. Trace it once, and it stops feeling mysterious. The residual enters the top linear layer, which turns it into the transpose of its weights times that gradient and records its own weight and bias gradients on the way. The tan scales what comes through by 1 minus its output squared. The bottom linear layer does the very same thing the top one did, one layer deeper. 3 layers, 3 backward methods we already wrote, and the loop is the only new line. We have hand-derived every gradient in the network. Which raises the only honest question left. How do we know we got the calculus right? We never trust a gradient we did not check. And there is a beautiful way to check one, using no calculus at all. Go back to the very definition of a derivative. Nudge one parameter up by a tiny amount, measure the loss, nudge it down by the same amount, measure again, and take the difference divided by twice the nudge. That central difference is what the slope numerically is. Do it for every parameter, and compare each numerical slope against the analytic gradient our backward pass produced.
If we can just compute it numerically, why bother deriving it by hand at all?
Because the numerical way is far too slow to train with. It costs 2 full forward passes for every single parameter. It is not the engine, it is the auditor. So we run it on the little network from episode 1. A linear layer, a hyperbolic tangent, and a second linear layer, feeding logits into a softmax loss. For each parameter, 2 numbers. The analytic gradient, straight from our hand-written backward methods. And the numerical gradient, from nudging the loss. They agree. The worst relative disagreement across every weight and bias in the network is about 1 part in 10 million. That is the green light. Our derivatives are correct. So why 1 part in 10 million and not exactly 0? 2 honest reasons. The numerical slope is itself only an approximation, so tiny rounding errors survive. And some activations are not perfectly smooth. The rectified linear unit, the other activation in this library, has a sharp kink at 0, a corner where it has no single well-defined slope. Land a value exactly on that kink, and the numerical check and the analytic rule can honestly disagree. That is why the tolerance is a small number rather than 0. Not sloppiness, but the truth about where a derivative lives and where it does not. From here on, this check is a fixture of the series. Every time we add a new component, we will derive its backward pass by hand, and then we will end by running the gradient check and showing this same green card. No autograd. No mystery. No trusting a gradient we did not prove. And the backward pass we wrote today does not change again. Every episode after this one reuses it, exactly as it stands, and only teaches the checking machine 1 new layer to check. We did not automate the calculus, we understood it